Hi, I'm Cameron Millard. I work for the Town of Vail. I'm a clean energy specialist. And I'm joined with my partner in crime here, Matt Garlick. Matt, can you introduce yourself?
I'm Matt Garlick. I'm a managing member of the Gray Edge Group. We are a national consulting firm specialized in thermal energy networks, and you'll know what that means after this presentation.
Sounds good. Well, we're delighted to be with you here today to talk about decarbonization and snow melting and geothermal and thermal energy networks. So we've got a lot to unpack, but we have an hour, which is wonderful. So we're going to get started here. Yeah, so let me talk to you a little bit about our decarbonization journey in Vail. Vail is an international resort destination with 3 million visitors annually, and it's a ski town, of course. And about 15 or 20 years ago, the town decided to put in a snowmelt system. The snowmelt system grew over time because it provided a lot of benefits to the guests and the visitor experience in Vail. Getting around without slip and falls. Plowing in Vail can be challenging. Where do you put the snow? Makes a lot of noise. There's a lot of cobblestones. It's hard to find enough employees to keep everything clean. So the snowmelt system provides a real service, an important service to the town of Vail. But unfortunately, it's the lion's share of our greenhouse gas emissions, at least from a municipal operations perspective. Our snowmelt system creates on average 6,500 metric tons of CO2 annually, which represents about 80% of the emissions that the town produces, not including transportation. So in Vail, we're lucky to have an electric utility cooperative, Holy Cross Energy, that has made huge strides in decarbonizing the grid. So we know that electrification is a solution to decarbonize our energy systems. And indeed, we have experimented with electrification, namely in the form of taking one of the smallest zones in Vail and putting it on an electric resistance boiler. So we're in the third year of operation with that electric resistance boiler. It's 440 kilowatt boiler. It's pretty hefty. And we have a little heat map here that shows the usage of that electric boiler. Each little square represents an hour of energy use across a week, and then going down through the months. So we've learned a lot with this electric boiler. One thing that's kind of interesting is electric resistance boilers give you the opportunity to turn it on and off that boiler. And so we've had some efficiencies. It doesn't have to ramp up like an electric gas boiler. But there are some downsides to electric resistance, namely the increased cost. Now, we took one of the smallest zones in the town. Normally, we'd spend about $15K to run gas through that boiler. And now we're spending about $45,000, so about 3 times the cost to run that electric resistance boiler. So we're wondering, is there a better way? And if we were to transition all of our snowmelt, by the way, we have about 12 acres of snowmelt, one of the largest in the world, probably in North America. Not sure if we should be proud of that or ashamed of that. But if we were to switch all of that to electric, it'd be equal to about 7 megawatts of power. Our electric resistance boiler, we had to upgrade the transformer and make other infrastructure improvements to make that possible. Expensive. Our utility was great in helping with that, but we're not sure that's feasible to expand to the full 12-acre system. So that's a little bit about where we've been and where we're going. We're really excited about it. When I first started in my role as a clean energy specialist at the town, I wasn't sure it was possible to decarbonize the town's snowmelt system. Now I truly believe that it is, and we're going to talk to you about that.
Okay. We'll get to the very professional graph here on the left. Give me a second. As we look to decarbonization, when you're considering the grid, the last 10% is going to be the hardest. You can add renewables, you can add wind and solar and all these great technologies, but getting to that base load, that last 10%, is of course going to be the most difficult thing that we have to do. And mountain towns have a very unique challenge. They're high up and it's cold, and heating dominated climates have traditionally not been well suited for geothermal type applications.
Say that slower.
Heating dominated climates
Yeah. Are not.
are not traditionally. I'll tell you why that's wrong in a second. But yeah, that's not been the case in the past. You add electrification to that, and the problems compound for the utility. How do we provide peak heating loads during the middle of the night when no sun's going and charge your EVs? So we need to look at electrification at scale. That's where this very professional chart comes in. This is what we call the Falcon curve, affectionately. The red line there is what if you took all of your building stock and converted it to electric resistance heating? What would the impact be on the grid over the course of the year? Catastrophic is a word that comes to mind. This is untenable for your utility to provide that much demand in addition to what they're currently trying to provide during the cooling season. So we look at a better technology. Air source heat pumps, this blue line. You have a COP of 2. COP is coefficient of performance. It's how many units of energy do you need to move additional units of energy, or how many units of energy can you move with one, rather. So another way to think of that is 200% efficient, right? Much better, still ridiculously higher than your summertime peaks that you would experience now. If you go to the ground, if you have a building connected to a ground source heat pump, well, now we're at a COP of 4, and it's getting closer to where your summertime cooling peaks were. But the secret sauce happens when you start networking buildings that are on heat pumps. A network system can see a COP of 6. And from a utility perspective, now we're in the realm of we're very efficient, and this is very doable given our existing power generation assets. So let's continue from this point by talking about what we're not going to talk about. We're not talking about geothermal power. When you talk to people, that's usually the first thing that they think of. Oh, geopower. You go down 2,000 feet, 5,000 feet, you put water down, you get steam back, you make electricity. That's not what we're talking about. The next thing we're not talking about is a district geo. If you have a campus, oftentimes there is a central plant, and they will have deep bore fields to generate power or to generate heat, and from that they can send it out like a regular heating hot water line. That's not what we're talking about. Building geo. This is a one-to-one situation where you would have a building like this, and in the field adjacent to it, you'd put geo down into the ground. What we're talking about this time is a thermal energy network, which expands on that idea. This is a collection of buildings, a neighborhood, a campus, a city block that are all on heat pumps that are able to trade heat among them, and we may have geothermal connected to it. It's not the defining feature of a thermal energy network, but it's an important one. So we'll start with the basics. I think I'm probably preaching to the choir with most of this. A heat pump is a device that moves energy from one place to another, right? We talked about this with the COP. When you network heat pumps in a building, well, now you can move energy from the lobby to the office, from the first floor to the 5th floor, from the south face to the north face, right? Your building becomes significantly more efficient. But when we get to a thermal energy network, now we're networking heat pump buildings. So this is the term, right? Thermal energy network. There are 3 main components to a thermal energy network. The first are the loads. These are just your buildings. Anything that has a thermal need, heating, cooling, domestic hot water. That's your residences, your offices, your government buildings, your airports, your industrial complexes can connect to this. The second part is the bit that connects them. And we'll call this a one-pipe ambient temperature loop system. Ambient, meaning it's a water pipe that tries to keep the temperature between 45 and 85 degrees Fahrenheit. All right, so it's not hot and it's not cool. This is the thermal highway where we move energy between the buildings and the next part, which are the thermal management assets. Thermal management assets can be anything that we can pull energy out of, put energy into, or store energy in. And this is where the ground becomes a really important potential asset. Again, we don't have to have this. If you're next to Lake Michigan, you might not need to put in boreholes. You just use the lake as your sink, source, and storage. But places like Jackson, there's ground underneath us, right? This is available everywhere you're going to have a building. And this is a place where we can usually sink energy into, source energy from, but most importantly, it's storage. Start thinking of the ground as a thermal battery. And that's important because when we generate heat, it's not always coincident with when we need heat. We're able to dissociate the generation from the load itself. And so if you had an asset like a solar thermal, obviously it produces heat during the day, and you might only need that at night when it gets cold, like on a day like today. If you have that thermal battery as one of the potential connected assets, well, now that's not a problem. And it's not just day to night energy storage. This can be seasonal. If we have a climate that's a little bit more balanced out, we're not talking Saudi Arabia here, you can reject heat, cooling is what we'd call that, during the summer and warm up the ground. And by the time November, December hits, that ground is in a much more conducive temperature for very efficient heat pump operation when you need the heating. So, thermal energy network is the parent. Ambient temperature loop is the very specific type of system that we suggest as the most efficient option you could go with. When you have one ambient temperature loop, connecting the next one is super simple. We call these microgrids. And if you think of one as a circuit, the next one as a circuit, you need a two-pipe connection between them. And now they can communicate thermally. We can, if one of them has a data center connected to it, right? That would be a great source of heat for a cold climate like Jackson, like Aspen, like Vail. Now that asset on one loop becomes an asset for the next loop. If you had a cooling tower connected to one of them, it becomes an asset to all of them. And so we're able to share assets, we're able to share heat between them, and the bigger they get, the more efficient they get. We often reference what we call the 50-90 rule. And this is ubiquitous. This is every climate zone in the world operates roughly like this. And what it says is that if you can meet 50% of your peak load, think of your coldest night in the middle of winter, 50% of that peak, if you can supply that with renewable sources, that decarbonizes 90% of your operational hours within the year. That's getting most of those low-hanging fruit. And we still may use a natural gas boiler for the remaining 10%, for that peaker. But we've got most of the decarbonization goodies by connecting a very efficient system with a more traditional system. Often we use that as a way to make these systems more affordable, right? Makes a lot of sense. The next bit is system diversity. System diversity is not required. You could connect one neighborhood to one of these types of systems, and it would absolutely work. But everybody needs heating at the same time, and everybody needs cooling at the same time, and there's very little overlap where you have the potential to trade heat between them. But as we're looking at putting one of these in a new system, we look at where could we design it to where it has a lot of diversity. The office and the library and the hospital and the townhomes. Because when we're able to connect a diverse group of building typologies, their more likely to overlap in when they're heating and cooling, so that the hospital can be rejecting heat in the late fall and the residences need that heat. We can just do a direct swap. Again, I'll stress here the importance of that thermal battery in the ground. We don't have to have it coincident if we have the battery as one of the connected assets. One of our favorite projects to talk about, this one's been going since 2008 at Colorado Mesa University in Grand Junction, Colorado. And this started out as one of those micro districts. And we connected buildings. They were all heat pump buildings. We connected them between them. We gave them a bore field, and it operated well. And then we added another and another and another, and now we're up to 5. And for those of you that are energy nerds like me, it's a 3,500-ton system, which is a lot of cooling. It's a big system, and it's looking to double the size given state and federal incentives that are available to it right now. The governor's very proud of this one. He likes to get up and tell other governors about what cool things are happening in Colorado. So again, this is a one-pipe ambient temperature loop system. It's just a circuit that goes around, and the buildings are able to reject heat or pull heat out of it as needed. Each of these blue fields are bore fields. They're invisible infrastructure. You would never know that they were there unless somebody pointed them out to you, because they look like a soccer field, right? And they're only connected by these pipes buried 5 to 10 feet down, and the water's pushed around by normal pumps. So it's an invisible system, but it seems to work quite well. We had a third party, or rather the utility commissioned a third party energy firm to come in and do a study of it. And what they found was that a traditional campus system would likely have a COP between heating using natural gas boilers and air source or water source chillers would have a COP of 1.9 across the whole year. What they found was that this system was operating at 5.7. That's a really good number. I don't know if you're nerds like me, but that is a crazy number. So much that I hit the wrong button. What's crazy about this is that in the buildings, the heat pumps themselves that condition your office or whatever, the sticker only says a COP of 4. So as a system, we're seeing a greater than the box efficiency on an annual basis. Another crazy thing that's specific or would be specifically valuable to mountain towns is the heating efficiency is 8.9 during the winter. I'm trying to tamp down my enthusiasm, but that's a really good number. That's an enviable number. I would suggest this system type is the most efficient that you could install with the technology that we've used. And this technology is state of the shelf. It's not state of the art. It's just pumps, it's just pipes, it's just water to air heat pumps like most of you have in the buildings that you're in every day. Some interesting numbers. They do have cooling towers connected. A traditional system would have used 14.5 million gallons of water evaporated out to keep it cooled. We only use 4.5. That's an improvement. We would have had a peak campus load of 784 kW. We're down to 185 kW. One of the most important ones I've highlighted there in green. If you were to do a one-to-one geothermal installation, like you're probably most familiar with, a geo-exchange system, you would have put in this geology 217 feet of borehole per installed cooling ton. Because of the diversity among the system, because of a more refined understanding of the properties of that ground battery, how fast you can charge it, how fast you can discharge it, how long you can store energy in it, we're able to get away with 84 vertical feet of borehole per installed ton. It's a 61% reduction. And you should read CapEx reduction there. 61% fewer boreholes that need to go in to satisfy this system. That's a big deal. And because of that, they're saving over $2 million a year in utility savings, and that's been enough that the university president says they're able to reduce their tuition by 2%. Kind of neat. For the utility nerds in the crowd, as the campus has grown. So this chart shows going from 800,000 square feet in 2013 to 1.2 million square feet of connected load in 2016. 50% growth. They've been able to maintain a 1 megawatt window across that entire time period, with a few exceptions like a new library coming on and the students coming back and everybody leaves the doors open. But that's a big deal for the folks that are providing power to us. Okay.
Thanks, Matt. That was a great explanation. So now we'll take it back to the Vail situation and the snow melt. Up here we have a map of our, let's see, this is either Vail Village or Lion's Head. I think this is Vail Village. And we have the snowmelt system. It's really big, and we have different snowmelt plants throughout the town. And we know that it's highly energy intensive. So we need a system that can meet that intensity. Matt talked about peaker boilers. They could be natural gas, they could be electric resistance. And that 50-90 rule really applies well to the snowmelt because of the temperatures that we're idling that snowmelt at. We don't turn off the system. We maintain a baseline readiness for snowfall for big snow events. Another thing that happens is in the late afternoon, things start to cool off. The sun's been shining. Now snow from buildings is melting and dripping, and that snowmelt system likes to rev up in the late afternoon, which is when the grid is under peak demand. I already talked about the expense of electric resistance and the system performance being a must. You know, when I was first hired, I said, well, this is an easy problem to solve. We just turn it off. It's like, no, we're not turning it off. But what we've learned is we can actually provide for that guest experience. We can have that snow melt and we can decarbonize it. So we can do both things. We have to be bold, though. We have to take that next step. You know, we've talked about campuses that have these systems. Well, now we're applying it to, you know, quite a large snowmelt system. But buildings are also a big part of that puzzle. And our thinking has evolved along these lines for a couple reasons. Number one, Matt alluded to the fact that buildings and thermal management devices are important for system performance. And looking around Vail, we have some excellent opportunities to take advantage of, including our Dobson Ice Arena. Has anyone been to the Dobson Ice Arena? It's the spiritual home of youth hockey, I've been told. It's a beloved building in Vail, and it's undergoing a major renovation, including new HVAC systems. Our library is nearby. The library is 40 years old. It's at its end of life as far as the mechanical equipment, so it needs a redesign and a refresh. Why not plug that into the ambient temperature loop and also provide heating for the library, which it really needs? So buildings also factor in because of the Inflation Reduction Act. And we don't know this for sure. We're going to work with some specialized consultants, some tax consultants. But the IRA is not for things like snow melting. Everyone knows what I'm talking about, the Inflation Reduction Act and the investment tax credit. So we need to get buildings into the action so we can reduce some cost. It'll be tricky. I don't know where the IRA applies and where it ends. But this is part of the exploration here that we're investigating. Next slide, Matt. So here's a little chart. It shows the snowmelt. It's about 80% of our municipal emissions. Fire pits are 1%, and people see the fire pits a lot, and they ask me, why are those on? You know, we should turn those off. Those are terrible. But they only represent 1% of our gas use. Buildings are about 20%. And it's the snow melt that's the big elephant in the room here. So besides thinking about a clean energy alternative, I think we're doing something that is also very impactful and important in this, which is how do we operate that snow melt system more efficiently? If we can shrink the energy intensity of that snow melt, it's less geothermal boreholes that need to be drilled. And indeed, we found many opportunities with the help of our consultants at the Gray Edge Group. During a retro commissioning process, we noticed, for example, that this infrared image was taken in the winter. I think it was late winter, but the sidewalk here is 103 degrees. And the sidewalk doesn't need to be 103 degrees to melt snow. It only needs to be 40 degrees. Now, there's a long story about why we run the snowmelt system so hot. It has to do with leaking and expansion tanks and chopping out controls to make it simple and make it work. It had issues from day one in terms of performance. So what has been driving our snowmelt program is let's make sure there's no slippery spots for guests to slip and fall. Lawsuits are expensive, and I get that. But when we find 103 degrees out there, it gets you thinking, you know, what are the opportunities? How can we shrink this thing down? One fun thing that we did was turn off the gas because we idle constantly and circulate the pumps. I'm sorry, you went ahead here. And we're calling this the solar idle mode. So can we move heat in the snowmelt system from warm, sunny areas to cold, shady areas without running gas and still kind of maintain that slab temperature? And we think we can. And in fact, we might be able to use the snowmelt system itself as a giant solar collector to charge up the ground during the summer months, which would be really cool, and to improve system performance during the winter. So that's one of many retro commissioning recommendations that came out of that study that we're trying to implement at the same time as develop the clean energy alternative. Okay, next slide. So it takes a lot of feasibility study to, advance a project like this, and drilling is really important. So we drilled some boreholes in Ford Park of Vail. It's a beautiful area, a beautiful town facility, and it was a little stressful. I'll be honest. We waited a little late, and so things got cold, and you need a lot of water for drilling. But the drill team was really remarkable. These are hardworking guys who do the drilling, and they overcome a lot of challenges, including having their keys stolen from their truck overnight. You don't think about Vail as a high theft area, but that was something they had to bounce back from, and they did. And so the graph on the right here is our thermal conductivity test, and basically what's happening is they're pulsing heat or energy into the ground through a loop that's been installed, and measuring things like thermal diffusivity, which is what is the ability of that ground to act as a thermal battery and store that heat. And the good news that came out of that study is Vail has very good geothermal resources to store heat and then collect that heat, for future uses. With the energy intensity of snowmelt, it's going to be very important to increase that ground temperature as much as we can all year round. There's a potential risk if you take too much heat out of the ground, things can freeze up. And so these implications are really important to investigate early on in the process. So we have some photos here. During our feasibility study, we walked all over town. We looked at all kinds of things, trying to identify where is the waste heat coming from that we can utilize. And this picture right here is the wastewater effluent pipe that discharges up to 4 million gallons per day from the Eagle River Water and Sanitation District. They're a separate entity, but in speaking with them, we learned that they are under a new regulatory imperative to reduce their effluent temperatures into the stream, into Gore Creek. The town of Vail has environmental goals around Gore Creek as well, that we're very proud of the progress there. But at any rate, they need to take some temperature out of that water. And to do that, they'll either have to build a large, expensive chiller plant or work with this project through a simple heat exchanger, and it could benefit the ambient temperature loop by taking heat out of that water. So I heard a great term this morning, multi-solving. This is a great example of multi-solving. We can solve their problem, we can solve our problem, everybody wins. And we're looking at other assets too. We've been in close conversation with Vail Resorts. So this is near some snowmaking infrastructure. What if we took a few degrees out of snowmaking water? That's less energy to chill it for snowmaking, helps them, helps the thermal loop. This is Lion's Head here. There's a beautiful hotel there. I'm told that they have the most expensive room in Colorado called the Arabelle. And the town has a cost-sharing agreement with the Arabelle to do a bunch of public snow melting out of that facility. I've been in their mechanical room, huge boilers. They have chillers in there. Chillers are important source of waste heat. So can we work with Vail Resorts on this project and solve some of their challenges and goals as well? By the way, that hotel is coming under the Colorado Building Performance Standards, which are going to mandate a reduction in energy intensity over time. So I think they're good for this next round until 2026, but over time they have to step it down. And you just run out of efficiency measures in a facility like that until you're talking about thermal energy networks. Here's our ice arena, and here's our library. And for me, it's been a really interesting shift in my perspective. It really opens your eyes to the waste heat opportunities out there. And it's just a different way of thinking about energy, which is really exciting to me. I've been in energy efficiency for 15 years, and this is something new to me. Let's take it to the next slide here. So I'm really pleased to announce that we have won an award from the Geothermal Energy Grant Program. This is offered through the Colorado Energy Office. And we got $250K. Now our budget is $500K for this next design phase. So our Vail Town Council has been generous and thoughtful in matching these funds, but we're really thankful to this kind of infusion of resources to do the design work so that we can have construction plans for this project. And we're calling it the Vail Civic Area Thermal Heating District. The Civic Area is kind of around the Lion's Head Village, if you're familiar with Vail. It's actually not our biggest snowmelt plant in that area, but it's proximate to the best thermal resources available, like the wastewater treatment plant, which also has connectivity via a bike path. And I'll have to take some heat when we dig up that bike path, but we'll put it back, and you'll never know it's there. Just a minor interruption, but the idea is to get a system going that we can then add on to with future expansion, and then tackle our big boiler plant at the Vail Village. And we've identified areas with good spacing for boreholes. That'll be another one where there'll be an interruption of services in Ford Park where we have a lot of playing fields, but it all gets put back and it's invisible. And that's the beauty of it. You know, Vail looked into a biomass plant a few years ago, and you know that means trucks and big facility and more impact. So this is a really nice solution, I think, to our problem. Next slide, Matt. So I'm going to hand it off to Matt. Matt and I have been talking to utilities. I know that this is not a utility focused conference, but the utility conversation is super important. So Matt's going to tell us a little bit about that.
So unfortunately, I don't have a clear path and solution to present to you today. But when you add a U to a 10, you get a U10, a utility thermal energy network. This is taking the concept of like what Colorado Mesa has done and making it applicable to someone like Vail or Jackson. And as I mentioned, this is an evolving conversation. We're still figuring this out, but it's being held with great fervor across the nation in our little niches. A lot of it centers around three ideas. Who's going to own it? Who's going to finance it? And who's going to operate it long term? And really there's three different groups that are kind of vying for those positions. One of them would be third-party energy groups, ESCO type companies, that are in a place where they could put in the infrastructure and sell you, the building owner, BTUs. Another one is the municipality itself. Those of you from municipalities or counties, you probably have a water division under your umbrella. This is very similar. We're just moving water around with pumps and selling, potentially based on the gallon. So it could be a good fit there. The third one is the utility company. Again, these are folks that already have the rights of way established. They already understand how to interact with customers, set up tariffs, and bill for something maybe other than kilowatt hours and decatherms, but call it comfort conditioning. And so any permutation of those three owner groups, owning, operating, and financing it, is viable. And we just need to figure out which one would be best for your particular town, your particular situation. Coming from a design consulting background, I'm going to give a plug here. You need to have the right people involved. You can't just take Joe Schmo engineer off the corner and engage him to design a thermal energy network. You need to have people that have experience with this and have learned those hard lessons along the way. You need to commission it. You need to make sure that the design intent is realized in the implementation. And then you need to make sure that it's set up to be controlled correctly and that control continues, as you get turnover in the operations group, like happens in every utility, in every facilities group. There's also a discussion about what are you selling? Are you selling BTUs? Are you selling time in? I think the easiest, the cleanest solution to this is gallons. Gallons are easy to measure. Flow meters are cheap, they're reliable. If you have that common ambient temperature loop and can keep it at a consistent temperature, then every customer has kind of an equal access to a certain level of efficiency. And if you can measure gallons going in and out of their particular building, you can bill them, and it's really is a viable utility for a town, a utility company that itself, or a third-party company to invest in.
You want to arm wrestle for this last one?
No, you're on.
Okay, so I think everyone's probably familiar with the term beneficial electrification. I mean, that really is the path to decarbonization. But this last 10% where we're talking about is hard to decarbonize loads, shifting to electricity, shifting to renewable electricity and renewable energy supply to power these big thermal loads in our mountain towns. I mean, what a monumental challenge that is. And the thermal energy network, it's a holistic tool. It's this multi-solving, I like that term, solution to decarbonization, to maintaining a high level of service, to cooling, right? We have to cool in our mountain towns now. So it really does, stream health, right? Lowering that discharge water, just phenomenal. And for the decision makers and the people who hold the purse strings, a low cost method of maintaining those services over time. It's important. That coefficient of performance, it's just remarkable. I mean, we at the Town of Vail purchase natural gas on the commodities market 3 years at a time. We have had ultra low natural gas, 40 cents a therm. That is doubling under our next contract. At that super low price of gas, we think it had cost parity with a thermal energy network. So now, with gas doubling in price, it's going to be there's gonna be an ROI. We're trying to figure out what that is, but I think the big takeaway here is thermal energy networks are a bit of a paradigm shift in terms of how we use and share energy. And I liked the discussion earlier today about going from I to we. So together in Vail, we can solve these problems. Together as a community, a larger community with Eagle County, they're also looking at a thermal energy network with the Carbondale project, if we're familiar. So we're not the only ones. And if we have multiple thermal energy networks decoupled from that green energy supply, so you don't need to produce heat at the same time it's being generated, now the utility has a powerful tool to manage that load, to load shave, right? The town of, Eagle County might not need the system on when the town of Vail needs it on, and by paying attention to that and optimizing at a larger level, there's a systemic benefit to the green utility grid that's just remarkable. And by the way, it's not skyrocketing electric demand when other things need it, like electric vehicle charging. So that's the paradigm shift. It's really remarkable to me. I find it. I'm just so excited to move forward on this project. We're going into the design phase now, and we would love to answer any questions and have further conversation. Unless, Matt, was there anything you wanted to end on? I didn't.
You did it beautifully.
Okay.
You did a good job.
We don't have to.
Yeah.
Yeah.
For a community that doesn't have any of this kind of infrastructure already in place and they want to get started with maybe the municipality being the owner and operator, I heard talk about like neighborhoods versus campuses. Where do you think might make the most sense to start for a community that was interested in that direction?
Do you have any?
With the feasibility study, of course. Says the feasibility salesman. The idea that we approach these projects with is let's take a very broad look to begin with, 100,000 foot level. See what your loads are. Do you have enough buildings close enough for this to make sense? Because there is a minimum viable size for this to make sense. If you have a few areas where you have buildings connected or that are close enough, which one would be preferable given the diversity of building types? Do you have a complex with offices and residences in them? That'd be a good place to start. And then we would do an academic review of the ground. I mentioned you don't have to have the ground as part of this, but it's really advantageous. Are you right next to a lake? What does do the academic papers say? What do the drilling logs in the history of the region say as far as the makeup of the ground? If that's a green light, then we can go to the next phase, which is a little bit more expensive, but gets us more detailed information about the ground, about the loads, about the potential for the system. And that's where we've been at with Vail, and it's been green lights everywhere. And so we'll move to the next phase, which is design.
I might add a little additional piece to that. So there's a utility, their gas utility in Framingham, Massachusetts.
Right.
And they're converting their pipes to an ambient temperature loop, and now they're going to be a thermal utility, right, utilizing these systems. And there's an equity piece here for communities, right, that want to decarbonize but have inexpensive heating and cooling. So there are models for that as well to look at. So this conversation goes, well beyond the snowmelt situation in Vail. Yeah.
How do you prevent or monitor groundwater contamination from all these subsurface systems? I've not known a snowmelt system that doesn't leak, so I'm just curious what kind of leakage issues you have with the Vail system and with new construction.
Yeah, so we leak, it's hundreds of gallons of glycol into the ground already. this system aside. The ambient temperature loop itself uses water, and the geothermal loops are water. And then, of course, you have refrigerants at the heat pump level in buildings. But the ambient temperature loop is very benign. That's another.
There's no glycol?
Ambient temperature meaning 45 to 85 all the time. And it's buried at a depth of at least 5 feet. So no matter where you're at, that's probably beyond your frost level.
Yeah.
Up into your building? Yeah.
Does that mean then all the Vail pipes have to be dug up and new ones put in?
Well, no, the snowmelt system itself would stay in place, and we've actually been making strides to stop that leaking. Apparently, there was metric and imperial fittings. This is what I've been told when it was installed that didn't join right. But we found other issues like an expansion tank issue that caused the system to add more glycol in and probably overpressurize it every time the temperature came down. So our facilities team said, that we can't ever let the temperature come down because then it leaks. Their theory was that the joints were swelling when it was hot, but I think we've disproven that. But that facilities team is also constantly fixing and digging it up. But yeah, the snowmelt system stays in place. The ambient temperature loop is separate. It replaces the boiler system, right? Yeah. Did you have a question? Yeah.
This is just me not being a geologist, but when you're paying for drilling tests, like how far does that test reach? Like, if you know in one part of town you can have geothermal, but 3 miles south you have no idea. Like maybe there's some other capital costs.
So this goes a little bit back to the discussion of what we're not talking about. We're not talking about deep geothermal, where you want to go down thousands of feet to get to high temperature geothermal resources. We're talking geo-exchange systems. And typically our target is 500 feet deep, which is readily available just about anywhere you go. It's not that hard to do. But going 500 feet deep, we are just looking for a place to push and pull energy. And different ground has different characteristics. We need to understand that. Most of the time, ground is very receptive to it. Sometimes you might run into things that could make that a less desirable resource. Like, we don't want to drill through granite because it's going to be really expensive, right? Or we might hit an artesian aquifer and it might be squirting out of the hole. Like, well, we can't use that now. So that's part of that investigative process and why we dip our toe in, 1 millimeter at a time. Francis.
I'd like to hear a little bit more about the existing snowmelt operation, and you mentioned an existing system recommissioning effort. Obviously, one thing was don't let the slab sit at 100 degrees, right?
Yeah.
And you also mentioned like not being able to turn the system off because you've got melting ice and snow that
Yeah.
kind of runs across
Yeah.
the sidewalk, which we've all seen. So I'm just curious, what were the biggest drivers in reducing the efficiency of those existing systems? And anticipatory things like, snow's coming, so when
Yeah.
you lower or increase the temperature, those types of discussions.
Yeah, great question. And one of the I'd say main challenges is just the siloing of our different town departments. So I'm in the sustainability department, and now I'm shining a big flashlight on facilities, and that's bound to make some people feel a little uncomfortable. But really, our system has been maintained over the years by local mechanical contractors, and they've been told make it work. And so one thing that happened that was disappointing, well before my time, was the original intent of the system was to have 50 zones with controls with actuators that could be turned on and off. Because the system didn't function at the outer edges of the system, they kind of chopped those zones out. And then if you are in the town, there are these manifold boxes everywhere, and the valve actuators and all the control wiring is underground, and they fill up with water, from the melting of the snow. So things corrode. So the biggest backward slide in terms of efficiency was the mechanical contractors coming in and simplifying it from 50 zone system to a single system. Now you have no control or flexibility. Like you wouldn't do that in your own house, right? If you had a boiler system, you'd want to have multiple zones. So that's a big issue. You know, finding equipment that's robust to live in these harsh environments. And then I think just this standard that we have that the snow needs to vaporize before it even hits the pavement. This is something maybe culturally that we need to work on. Like it's a high alpine environment. Let's put some signs up. Let's do, you know. And you know, there are Vail locals who lament the loss of like snowy streets, right? You go to Vail now, it's just, you know, it doesn't even look like winter sometimes. But yeah, there's probably more details in that. I think, you know, the operational efficiency is getting better, but we have to keep the pressure on and keep it moving in the right direction. And that might mean taking a little bit of a risk every once in a while. Where like, you know, I don't want anyone to have a slip and fall, but this is a very important issue, and we need to balance these concerns. So this is a conversation I'm hoping we can have with our decision makers as well. Yeah.
Getting political, this is a generalization, but I find speaking to a more conservative mindset that they are most open to nuclear and now geothermal, and especially geothermal exchange systems versus wind and solar. Not this is hydro, all the other ones around it, not including those. Why is that? Because geothermal is not cheap.
I don't know, but maybe it's because it's drilling. It's something we're already good at. Drill, baby, drill, right? It's not such a simple shift. I've learned. I asked the drilling company that we worked with about this, and they said, you know, our processes are different enough that it's not a super clean transition from oil and gas, say, to making, you know, just you don't just flip a switch and have the workforce move over. But there is an interesting kind of exchange of information. Like drilling is very advanced in this country, and these fracking techniques and other things, they have implications for geothermal. So maybe that's it.
Transition.
Yeah.
I have a fairly niche comment, but I run a hot springs here locally called Astoria Hot Springs, and I'm also on the board of the International Hot Springs Association. And I'm just curious about these heat transfer systems and if there's any sort of integration that could happen with hot springs properties as they're dealing with cooling down water and also oftentimes putting water into high mountain streams as they're trying to get cooler before they get into those streams.
You're speaking my language. I love it. No, I mean, what you're talking about is a waste heat stream.
Yeah.
If you're trying to cool down natural hot water
Yeah.
to fit whatever EPA regulation, it's a waste heat stream. You're paying money to get rid of energy. Give it to me. I want it. You know, we can put that to work and improve the system efficiency.
Yeah, so when we talk to our members about it, I think cost is the biggest barrier, and then also potentially the fact that they're only looking at like a closed loop system. How can they use their heat to heat their buildings or use for their snowmelt? And so they're not finding the efficiency of cost that maybe.
That's a nuanced question,
Okay.
right? There's a lot of things that would go into whether or not that's cost effective. If you have to retrofit the entire building system for this one set of free heat, we can look at the economics. I can't tell you it'll be a slam dunk, but
I mean, there's so many different properties all over the country, though.
yeah, absolutely.
Kind of a tea leaves question, like looking 20 years down the line, are you seeing anything with technology integration that might present some interesting opportunities? I mean, like discharge low-head hydro or micro hydro systems where you can kind of pair this with other current or future technologies to enhance efficiency?
Cool story I've got for you. We're doing one of these at Steamboat Springs, right? And this is a geo exchange system coupled with the snowmelt system, but we're also looking to connect to the hotels. It's all very exciting. But also on that same mountain, they received the same grant that Cameron did to evaluate what's called an enhanced geothermal system, which is their particular flavor of that is that you drill down 2,000 or 3,000 feet, put water down, steam comes out, you make electricity. From that, we can cascade thermal energy. They can't do anything with 150-degree water to make more electricity from it. But that's a gold mine for me. So anywhere where you have geopower applications and it's close enough to building loads that need that, boy, pairing those two would just be a match made in heaven. It's free energy, right? You're making electricity, and from the waste of that, you're cooling or you're heating your buildings. It'd be beautiful. So as an example, the answer was yes. Technologies are going to evolve to make this pair well with some of the things that are being evaluated. Yes, it is.
I have just a question about the footprint, like in your networking, how close or far away are the buildings that you're networking? I don't recall what the distances were.
That's a question of economics. On a campus, it makes perfect sense, right? They're right next to each other. If I had a hotel and a bunch of townhomes all connected, and there was a power plant with a waste heat stream a mile down the road, well, I would want to say, what resources do I have more local? How much is it going to cost me to get to those BTUs versus running a mile or 10 miles to get to these other BTUs? There's more of them over here, but it's a bigger expense to get to it. So it's a question of economics. It's a question of going after the least cost path to conditioning your building.
I had a question just on the drilling, and this maybe is kind of given in a feasibility study, but being in a town where often once ground is dug into, things like mining tailings show up, is that like a no-go the instant that's found, or how does that?
No, when you're drilling, if you come up with mining tailings, soils that are less desirable to have on site, we just remove them. We put them to a remediation site where they can be handled properly. Once we've got the hole, you put a U loop down into it, HDPE pipe, one that goes down, one that goes up, and then you put grout around it. There's no transfer of water between these. You're not using the water in the ATL to go to the groundwater. It's just a one-time boring. You grout it in, and now you're just moving energy. And then, as I said, you handle the tailings as is necessary.
Time for a couple more.
Is there a minimum peak load that you're looking for these ambient systems?
Our rule of thumb is 300 tons. I know you're a nerd, so yeah, that's it. Any other questions? Did I get them all? One more.
One quick one. There was a resource for those of us who are not nerds. Where's one place you could direct us where we wanted to learn as much as we could about the different energy systems?
Heat.org. HEET.org.
Great question. Thank you all so much. Really appreciate it.